Good morning. In this lecture video, I'm going to explain excitation table. So, as in the previous video, we constructed transition table from transition expression. So, in this, I'm going to explain how do we construct excitation table and what is excitation table. See, excitation table. So, in the previous we constructed transition table from transition expression, and an alternate approach to construct the transition table is first to construct excitation table. Okay, transition table was constructed by substituting excitation expression into flip-flop characteristic equation. So alternate approach is to construct first excitation table from the excitation and output expression, and then from excitation table we can construct transition table. So again, excitation table consists of three sections: present state section, excitation, and output section. Output section. So here excitation, so present state and output section are same as transition table, and the excitation is analogous to next state section. So in transition table, using excitation expression, it is analogous to next state section in transition table, and it is constructed using excitation expressions. Okay. So excitation section again consists of one column for each combination of external input variables. Now let's see excitation table for Mealy network. So this is the excitation table. First section is present state. So these are the state variables. Since two variables are there, four possible combination. In compared to the transition table here next state was there. Here it is excitation D1 and D2. For the Mealy network, since D1 and D2 are the flip flops. So again it is divided into two columns. When x is equal to 0, x is equal to 1, d1, d2, d1, d2, and output. So this output is same as transition table. Okay. So to complete this, we need to consider excitation expressions. These are the excitation expressions. So as we wrote next state, similarly here we write excitations. Excitation by substituting x is equal to 0 in d1 expression, it reduces to q2 bar, q1 bar, q2. So d1 will be 1 whenever q2 is 0. See, whenever q2 is 0, 1, 0, 1, and this term will be 1 when it is 0, 1. So 0, 1 it is 1, the remaining it is 0. Similarly, when x is equal to 1, so first term becomes 0, second term will be present, and this is 1 when it is 0, 1. When it is 0, 1, it is 1, the remaining combination is 0. And for d2, by substituting x is equal to 0, first term becomes 0. So the reduced expression is q1 bar q2, and this is 1 when it is 1, 0. Sorry, 0, 1, 0, 1. So when it is 0, 1, d2 is 1, the remaining combination it is 0. And by substituting x is equal to 1, d2 reduces to q1 bar plus q1 bar q2. So it is d2 is 1 and 1 is 0. First two combination it is 1. And second term becomes 1 when it is 0, 1. When it is 0, 1, it is 1. So the remaining combination is 0. Okay, this is the right excitation sections. And output section is same as we analyzed in the previous when constructing transition table. Clear now? Similarly, for Moore network, these are the excitation expressions and output. Just I copied from the transition table. See, excitation section means here since we use JK flip-flop, J1 K1, J2 K2 are the excitations. When x is equal xy is equal to 0 0, J1 K1, J2 K2. When it is 0 1, J1 K1, J2 K2. When it is 1 0 and when it is 1 1. Okay. See, J1 is equal to y irrespective of, it is independent of state variable and x. State variable and x. That means here J1 is equal to y. Here y is equal to 0. So it is 0. Correct? And see here y is equal to 1. So it is 1. And see here y is equal to 0. So it is all 0. See here y is equal to 1, so it's all 1. Clear na? But k1, it depends on both x and y. So substitute x is equal to 0, y is equal to 0. So it becomes, see, y is equal to 0, x is equal to 0. So k1 becomes 0. K1 becomes 0, all zeros. Correct? And when xy is equal to 0, 1, so y is equal to 1, x is equal to 0, it becomes 1. Correct? So for all the combination it is 1. And similarly, when it is 1, 0, so y is equal to 0, correct? X is equal to 1, it reduces to q2 bar. Q2 bar. See here Q1 is Q2 bar. Here Q2 is 0, 1, 0, 1. It is 1, 0, 1, 0. Similarly, by substituting this, okay, it becomes 1 plus Q2 bar. 1 plus Q2 bar. That means it is always 1 because one term is 1. Na? So it is always 1. Okay. Similarly, J1 expression, sorry, J2 expression. J2 expression. Okay. See. J2, when you substitute xy is equal to 0, 0, first term is 0, second term is also 0. So J2 is equal to 0. So here are a 0. And when you substitute 0, 1 here, so first term is 0, second term is present. So it is equal to Q1. It is equal to Q1. See, it is same as Q1. 0, 0, 1, 1, 0, 0, 1, 1. And when you substitute 1, 0, in J2 expression, the first term is present, second term is absent. So it reduces to Q1 bar. See here, Q1 is 1, 0, sorry, 0, 0, 1. It is 1, 1, 0, 0. Q1 bar. Similarly, when you substitute x, y is equal to 1, 1, first term will be present, second term is absent because x is equal to 1, x bar is 0. So again it reduces to Q1 bar. So it is Q1 bar. Clear na? Similarly, J2 in this expression. So substitute xy is equal to 0, 0. First term is 0, second term is 0. So it is always 0. It is always 0. And similarly, when you substitute 0, 1, first term is 0, second term is present, Q1. So same as Q1. Same as Q1. Okay. So when you substitute 1, 0, first term will be present. Means 1. X is equal to 1, y is bar is equal to 1. So second term is 0. So it is same as, means it is always 1. It is always 1. And when you substitute xy is equal to 1, 1, xy is equal to 1, 1. So first term is absent, means 0 because y bar is 0 and second term will be present. So it is Q1. It is Q1. See, same as Q1. 0, 0, 1, 1. Is it clear now? So this is how we construct, and this is the complete table. So this is how we construct excitation table from the excitation expression. So it is analogous to transition table. So present state section and output section are same. Then excitation section is analogous to next state section, and that is constructed using the excitation expressions. So in the next video, I am continuing how to construct transition table.